We're gonna publish this as well. Oh, it's already published, okay. And I'm gonna send this to, where is it? Here we go. Nobody gets that? Come on, guys. What are you up to? Let's see what's going on here. So notification. Bullshit. All right. Okay. There we go. Let's go back here. And there we go. Did someone guess? 0 viewer guessed. Come on. Alright, let's do the next one. Oh, this one is difficult. Oh man. This is gonna be difficult. Oh my gosh, what am I even doing? What is that? No, that's. I don't think if anyone can guess this. Let's try again. Okay. And then. Oh wait, why did it change? Oh, I clicked on change. Sorry. So, let's see what's the. Oh, okay, this one. See if you can guess this one. This one should be easy. You need to type what you think it is. Guess what it is. Alright, let's see what we want to watch. We need to start this as well. Let's see how many. Impressions we got here. Okay, one, not too bad. Alright, let's see. It's getting hot. 6 bad and dangerous geoengineering ideas meant to cool down Earth. That would be interesting. Let's see what it has to say.
Oh, hey, look, it's Joe Scott, that other YouTuber that also talks about stuff I talk about. Haha, just kidding. He's actually pretty cool. Anyway, recently he made this video that you can find in the description with some direct
probably
title,
yours guess.
the absolute worst
Alright, we're
climate
gonna
change
stop
solution
for now.
possible.
Nobody's guessing
And you can
anything.
sort of see the solution right
Let me
here
know
in
if
the
you want to play
thumbnail,
again.
slowing down the Earth. And just to spoil his video, in case you're not going to be watching it, he basically explains that it's not a good idea and what would happen to Earth if we did slow it down. The effect would probably be quite the opposite. And then I suddenly realized, wait a second, I've been actually collecting a lot of these strange, unusual ideas and explanations on what we can do scientifically to prevent climate change for basically several years now. And in just the last few months, there actually have been two other propositions that kind of take the cake for being even maybe a little bit crazier. At least when it comes to the question of, let's solve the climate change by doing something absolutely ridiculous. And so in this video, basically let's explore these crazy propositions that I guess scientifically do make sense, but also really don't. They really do not make much sense at all. Usually for one simple reason. Even though they might lower the temperature of the planet by like 1 degree or 2 degrees, they'll actually end up destroying the planet in a completely different way. And so without further ado, let's start with the first one. Now this one is probably not the worst, and you might have heard of this one before, but essentially it would involve similar components to what we usually find in volcanoes. Here we're talking about things like sulfur dioxide. With the proposition being really simple, can we basically just spray it somewhere in the upper atmosphere using a lot of different airplanes, thus producing similar effects to what we usually expect from a typical volcanic eruption, which generally does lead to a slight decrease in temperature, mostly because of the effects of sulfur dioxide, as it essentially blocks some of the sunlight, preventing it from reaching the surface and from cooling out the planet. And there's of course at least one startup that already is trying to do that as well. Make sunsets. It's actually two dudes trying to launch a bunch of balloons filled with sulfur dioxide to have it delivered into the upper atmosphere. And the thing is, a few years back, similar ideas or potential experiments have been actually banned in countries like Sweden. And so this startup unofficially, or technically illegally, conducted their experiment in Mexico, which led to Mexico banning future experiments of similar type. And so basically here, most governments and technically most scientists don't really want to try this because we don't really know what it's going to lead to. Obviously it might lower the temperatures a little bit, but at the same time, sulfur dioxide also destroys ozone. So yeah, it's quite a big trade-off. Also, as far as I know, that's basically the premise of Snowpiercer. Their icy world was created because of similar experiments. And as far as I remember, people actually become cannibals in this movie. I don't want that. I don't want to eat anyone. So yeah, launching balloons or airplanes releasing sulfur dioxide, maybe not the smartest idea. But similarly, there have been other propositions of maybe just increasing the amounts of clouds. Clouds are white, they basically reflect some of the light, and increase the total albedo of the planet, thus cooling down things in the process. And cloud seeding, or weathermentification, is something that's been used for decades now, and is definitely actively used in a lot of different countries. There's an older video in the description that describes a lot of this in detail. The problem is that here, if we use things like airplanes, we would need a huge amount of airplanes pretty much flying every day, trying to produce clouds in certain regions. And ironically, just by flying those airplanes, we're dramatically increasing the overall emissions from those airplanes, possibly even counteracting the effects from the clouds. Now, alternatively, it's possible to use maybe ships, which actually has been proposed by several studies, with at least one study from the Royal Society, suggesting we can produce these specialized ships that could basically produce clouds simply by swimming around. But in this case, we would still need at least 1,000 of these. They would have to be active at all times. And at the same time, because they would be evaporating a lot of water, here the effects are once again somewhat difficult to predict. All of this evaporated water is also once again a relatively potent greenhouse gas. So we don't really know if those ships are going to produce clouds or just more vapor. I mean, it's definitely not the worst idea, but yeah, not the best either. But here's an idea that's a little bit cheaper and also possibly even not that bad, using plankton. Plankton is actually a huge carbon sink on planet Earth, and as these tiny organisms replicate, they often absorb huge amounts of carbon. Some of them also produce huge amounts of oxygen. And so by using things like, for example, pumps, it might be possible to encourage the growth of plankton by basically pushing huge amounts of nutrient-rich waters into much colder depths of the ocean in order to mix the water and in order to encourage plankton growth. And interestingly, these extremely large blooms of algae and plankton usually happen after major volcanic eruptions. Here's one after Tonga. This is like hundreds of kilometers in size. And so creating something like this artificially has a chance of dramatically reducing carbon levels by turning it into actual little creatures. But obviously this is not without problems either, because some of this bloom has a tendency to be toxic to other life. And at the same time, by encouraging growth in certain biomes, it might completely destroy the ecosystem. So here the long-term effects are completely unknown. Okay, this kind of an experiment would be kind of interesting to try on a much smaller scale, just to see what happens, but I would definitely not use this on a planetary scale in order to try to reduce the temperatures. Here's actually another somewhat unusual proposition. Arctic Ice Project. The point here is to spread tiny glass beads that you see right here on top of the surface of ice across the entire Arctic. And if you are asking why, I mean, the answer is pretty obvious, right? Wait, hold on, what is the answer? Oh yeah, that's right. It's to make things more reflective. It's to create more albedo. Less sunlight absorbed, less ice melted. By having ice absorb less sunlight, we expect it to melt less. And according to the website, it's actually already being tested somewhere in Norway. Okay, cool. I guess we'll see how that goes. Although somehow, I'm not sure if putting tiny pieces of glass across the entire Arctic is going to do wonders for other life. I mean, we already have microplastics pretty much everywhere. Now we're also going to have microglass beads. So not entirely sure where all of this goes just yet, but I guess we're going to find out in the next few years. But all of these previous ideas were kind of on the older side. A lot of them have been talked about for months or even years, and as I mentioned, some of them have already started their initial experiments. But in the last few months, we also got these two somewhat brand new ideas that I also wanted to talk about because, yeah, we probably shouldn't do those either. Okay, the first one is kind of intriguing, but intriguing for different reasons. It's based on a concept known as space sunshade or sun shield, a somewhat old geoengineering idea that basically suggests we can change the temperature of the planet by either amplifying or reducing the amount of sunlight by placing an object in one of the Lagrange points, specifically L1, located between Earth and the Sun, the point that is usually used for various solar telescopes, and by then essentially having something either create a sunshade, reducing the total sunlight, or amplifying sunlight in certain locations. But the previous problem with this proposition was that, well, first of all, this particular shade has to be really large, and second of all, the pressure from the sun itself, at some point, might completely dislodge this sun shield, making it somewhat impractical because it's not going to stay in a stable orbit for a very long time. The solar pressure is powerful enough to actually nudge certain objects by quite a large amount within just a few years. But this brand new paper from July of 2023 potentially solves that issue, introducing a tethered asteroid. Basically, a sun shield attached to an asteroid that acts as a kind of a counterweight. Okay, honestly, this one kind of made me giggle. It looks like a little potato flying a kite. And I guess in theory, this could maybe work to some extent. So basically here we have our sun shield that would block some of the sunlight, reducing the overall temperature on the planet. And because it would be attached to a relatively massive asteroid, the solar pressure in this case would not have as much effect, but it would still have some effect. As a matter of fact, the Yarkovsky effect that usually pushes asteroids around is powerful enough to change the orbits of asteroids after a few years. It's actually the reason why we usually cannot predict the exact orbits of various asteroids for longer than a few hundred years. And so even here, after some time, this whole thing is still going to be moved by the pressure from the sun. It's probably going to take longer than just the solar sail itself, but it will definitely happen, thus reducing the effectiveness of the entire process. On top of this might happen. And that is not something we would like to happen. Also, moving an asteroid in a different orbit is definitely beyond our current abilities. The DART mission that was successful in 2022 nudged a much smaller asteroid by a tiny bit. In order to move a larger object from, for example, the asteroid belt into the L1 Lagrange point, we will definitely require some super advanced rocketry that we currently do not have. Lastly, in order to even make a big enough sunshade, we still have to have an object that's probably going to be at least 3 million tons in mass. And so unless this is produced in outer space, placing this in orbit would be extraordinarily difficult. It's approximately as massive as 500,000 James Webb Space Telescopes. And that's of course not including the cables, which would also be required for all of this to work. So yeah, cool proposition, definitely a cool picture, but the kite flying potato is probably also not going to work either. And then we come to the final winner, the best idea, the worst idea. Although once again, the idea that's based on clever science. But before I talk about it, I wanted to briefly mention actual scientific paper that was recently released that uncovered unusual color changes on the entire planet. The oceans on the planet seem to be also changing in color as a result of climatic conditions. Now things are basically turning a little bit more green and possibly a little bit more turquoise. Although here I guess I'm oversimplifying things. The color though is definitely changing. And what's intriguing here is that we know that the color of the planet affects how much heat it receives. It basically affects what's known as the albedo. You can learn about this in the description below. Now more albedo, it means more reflectivity. Based on this particular study, we're not entirely sure how the oceans are changing yet, or basically we don't really know the exact albedo changes, but there might be a chance that the oceans are going to be a little bit more reflective, not less reflective. Anyway, these are definitely interesting discoveries and definitely good science. Most of these changes are a result of phytoplankton, which increases the overall amounts of chlorophyll. And intriguingly, approximately 56% of all oceans changed color. But can we maybe artificially change color of the planet in order to obviously increase albedo? What a good idea, right? Yeah, maybe not. Well, at least one study that you can find in the description makes a proposition about that as well. And I mean, this is a really big if, but just bear with me here. What if we paint the planet white? And I wish I was kidding, but this is a legit proposition with actual calculations and science behind it. And to some extent, it's actually based on the recent discovery of the whitest paint ever produced. It's able to reflect approximately 98% of light. Okay, so if we take that and then basically spread it in certain regions of the planet, in theory, it will make the planet reflect more light. It will definitely increase the albedo. In practice though, we basically are talking about covering approximately 1% of surface, or the entire Sahara Desert, or I guess parts of Australia, in this super white paint. Rough calculations suggest that when you
that's fine. I like it. That's fine. Let's
or
keep
about
it.
200,000 Olympic swimming pools. In other words, you would need a lot of paint. And yeah, obviously someone will have to do it as well. Here it actually reminded me of that famous scene from Spaceballs when they're combing the desert. And so yeah, theoretically, we could use the super white paint to paint the planet white, making it a little bit more reflective, and thus reducing the overall temperature on the planet just enough to mitigate current climate problems. But on the other hand, by doing a quick napkin calculation of the actual production costs of all of this paint, it becomes obvious that even producing this paint would be ridiculously expensive, would involve insufficient dyes and insufficient materials, and would very likely affect the climate negatively in many different ways. For example, there's only like several million tons of titanium dioxide produced annually, and that's what's usually used in a lot of white paint. Trying to figure out how to make billions of tons of this would be somewhat challenging. And more expensive, more advanced paints would obviously require even more. And so painting the planet white is, in my book, probably the
That's good. I like this so far.
At least in terms of human engineering ideas. But you might also want to check out that video by Joe Scott just to see his take on this as well. Anyway, at least for now, well, that's kind of all I wanted to mention.
Alright, yeah, that was...
collecting these studies.
Whatever. Should we watch some scammer videos? What is there? 17 years. This is Stephen the Second Law, Mystery of Entropy. Finally solved after 50 years. Let's watch it.
It is, but please be as technical as possible. We love the detail.
All right, okay. I don't think you really quite want that, but I'll go a certain distance.
The last one was amazing. I don't know if you saw, but it got over 500,000 views, the last one. So this is...
Yeah,
I'm over the moon with it. Thanks to you. Okay, so I'll crack straight on. MLST is sponsored by Numerai. Are you a data scientist looking to sharpen your skills against the best minds in the world? Numerai is a hedge fund which is driven by models created by data scientists like you. They give you immaculately squeaky clean stock market data which you can train your models on, and if your models do well, you get paid, which is nice. See the link in the description. Cheers. So last time I was slated for making my introduction too long, so this time I'm going to keep it brief. Not least of which because our guest is perhaps the most recognisable and brilliant scientist alive today, Dr. Stephen Wolfram. Now, being an experienced podcaster, I have a bit of a sense When I come across a scientist with a truly phenomenal intellect, and Stephen is this person. The only other candidate for me would be Yoshua Bach. And by the way, I'd love to host a conversation with you and Yoshua at some point in the future. I did ping him last night on Twitter, and he said he would be game. But anyway, I was listening to one of Dr. Wolfram's recent podcasts earlier today, and his insatiable hunger for knowledge was abundantly clear. He was recording that show at the end of last year, talking about researching his new book, which we're going to talk about.
Like the show,
he was pouring through ancient manuscripts, studying the etymology of words used to ascertain exactly what those early scientists were conceiving of, several of which remarkably were seeing the universe as a kind of discrete particle system, decades or even hundreds of years before it became accepted canonical knowledge. Now today we're going to discuss some of Dr. Wolfram's work on the second law of thermodynamics, which is to say the dynamics of heat. And frankly, our understanding of this phenomenon hasn't really changed in over 100 years. So, Dr. Wolfram remarked in his book that there's still something deeply mysterious about the second law. It seems like it's going to be provably true, but one never quite seems to get there. We're still missing a little something extra. Now, Dr. Wolfram's quest to understand the second law has been a 50-year story, and now finally, given his many breakthroughs on his computational physics project, we can finally start to, pull the pieces together and construct a proper framework to explain why and to what extent the second law is true. Now, don't worry, folks, we are going to get some AI questions in later, but Dr. Wolfram, it's an absolute honour to have you on the show. Thank you so much. And can you sketch out some of the details of your new book?
Yeah, well, let's see. Talking about the second law, one of the things that's fun and interesting is, it turns out probably some of the things that we're learning about the second law are actually relevant to AI and LLMs. See, I think one of the things that is an emerging interest here is what we might call LLM science. That is, and we're going to talk about the second law, but let me just make a few comments to begin with here. That you get an LLM, you train it on billions of web pages, then you discover that it has all kinds of behaviors. And the question is, what can you generically say about those behaviors? It's a little bit like saying you've got a bunch of, trillions of gas molecules in a room, and they're all bouncing around, and what can you say in the aggregate about their behavior? It's sort of a somewhat similar kind of question. But in the case of LLMs, we're things like, how does zero-shot learning, how does that work? Why does that happen? Why does anything like that happen? Why does it turn out to be the case that if you take the temperature, if you're using an LLM, the temperature is kind of this parameter that says to what extent, how are you going to, which word are you actually going to use out of the ranked list of words of different probabilities? Temperature 0 means you always pick the word that is the one that the LLM thinks is the most likely to come next. Temperature 1 means you pick them according to the probabilities that the LLM says they should occur with, and so on. And one of the things that one observes is, as you crank up the temperature, like for GPT, for ChatGPT, I think it's around 1.2 is the critical temperature. As you crank up the temperature, the LLM goes from talking sense to talking nonsense. It's a kind of a phase transition, like the transition from something like water to steam when you go above 100 degrees centigrade. One doesn't understand that transition yet. That's an example of a kind of a place where kind of the ideas and methodology of something like statistical mechanics is likely applicable to LLMs. The thing that's weird about LLMs is while all those gas molecules bouncing around, they don't have particular labels. They're not, the science of food. They're not they don't have a meaning to us humans. Where the things that we put into LLMs are things that sort of we think of as meaningful, we think of as being kind of the knowledge of our civilization. And the fact that when you put all of those together in this big kind of vat, you get certain kinds of emergent behaviors is an interesting thing. That's kind of this emerging area in a sense of LLM science, which I think is going to be quite important to understand. I mean, there are things we start to understand about scaling laws and so on, but I think that that's a key thing to understand in terms of the very practical issues about, how small can you make the LLMs? What are the LLMs really doing? Where can they just make use of computation? That's sort of the back end of the LLM. Okay, now now let's talk about the second law of thermodynamics. So what is the second law of thermodynamics? It's the sometimes called the law of entropy increase. It's kind of the law that says when things start off orderly, they tend to end up more disordered. So for example, if you take something like a bunch of gas molecules, and they're all initially sort of all in a clump, they're all kind of lined up, and then you just let them bounce around a box. Before too long, they'll be bouncing around kind of randomly. So that's characterized by this idea of entropy. So what is entropy? Entropy is basically counting the number of states of a system that are consistent with what you know about that system. So for example, if all you know is the gas molecules are all just in this box, there are many possible configurations they could have. If you know that the gas molecules are all in this particular corner of the box, there are fewer configurations they could have, because all the configurations that have gas molecules not in that corner can't be there. So entropy is the logarithm, basically, of the number of states that are consistent with what you know about a system. So to say that the entropy increases, which is another statement of the second law of thermodynamics, is to say that things essentially look more random to you. Because the things that you might say, oh, it's special, the system has these special characteristics. Well, if the entropy is increasing, it's saying that it's always sort of escaping from that specialness. It's always more typical, less special, so to speak. So the question has always been, why does this really happen? And here's why it gets tricky. Let's say you're talking about gas molecules. Well, if you knew the initial configuration of all those gas molecules, you just use Newton's equations and so on, Newton's laws, you figure out how these gas molecules bounce around, you know exactly where they're going to land up. There's no question of saying, oh, the thing got more random, we don't know where the gas molecules are. Well, no, you actually know exactly where the gas molecules are. You just follow the equations of motion to see where they go. So what is the, so how does it come to be the case that we can start to talk about entropy increasing? Well, people have said for a long time, what you really need to look at is the coarse-grained entropy. That is, you need to say not what particular configuration of the gas molecules end up in, but is that configuration in some way special? If at the beginning it was special because all the gas molecules were in the corner of the box, does it remain special later on? Okay, so the big observation is it doesn't remain special. But it's been very hard to characterize what that means. And here's sort of an analogy. If I should explain another thing. Another feature of this is a complicated subject, by the way, and another feature of this is that the thing that
the people
is this
around
notion of irreversibility, the notion that things might start orderly, they end up disordered and never go back. So, for example, you might have a mechanical motion where you're moving this big piece of metal or something that has gazillions of molecules in it, and you're moving them all together. But then some of that motion gets converted through friction into heat, and the sort of energy associated with the heat is something which is just a bunch of molecules randomly bouncing around, and you never kind of can get that back into something orderly. Once the motion is sort of turned into heat, turned into the randomness that's associated with heat, it never goes back into something more ordered again. And that's what, that's kind of this phenomenon of irreversibility, that things sort of irreversibly degrade into sort of randomness and sort of pure heat, and they never go back the other way. So again, and now why is that confusing? It's confusing because if you look microscopically at these individual molecules, each individual molecule, each individual collision, you could reverse that collision. So if you had a movie of the individual collisions, you show the movie, you can't tell whether the movie is running forwards or backwards because every individual elastic mechanical collision can be reversed. So the question is, why is it the case that in the aggregate, all of these things end up seeming like they're going irreversibly towards heat and never coming back from heat to sort of mechanical work? So this is kind of the mystery of all this stuff. And what has sort of come out is, I think we now understand how this works. I began to understand it back in the 1980s. I think I now really understand it. And I'll make a few other comments about it before sort of really trying to explain how it works. I will say that the first serious science project I tried to do back when I was 12 years old was about this very topic. So I'm now at T plus 50 years in trying to understand how this works. And just to tell that story, it's a little bit of an amusing story. I mean, I was interested in physics, and so I went and my big excitement from sort of finishing elementary school was go get a bunch of physics textbooks, and one of them had this cover picture that showed a bunch of sort of simulated particles that started on one side of a box and then kind of randomized and filled the box. And I was like, this is cool, and I read the description of the second order thermodynamics that's in that book, and I was like, I don't really understand how this works. Let me try and get a better understanding of it. I thought, okay, I had just sort of found that the school that I was going to had a computer. It was a thing the size of a desk, programmed with paper tape, with a whopping 8 kilowords of memory, ferrite core memory. But I thought, okay, I'm going to program this thing, just like whoever programmed it for the cover of the book. And I only learned many years later the story of how it got put on the cover of the book. It was actually, at the time, it used the world's largest supercomputer to do those computations. But I didn't know that at that time. In any case, so I said, I'm gonna do this simulation of these things. So there I am writing in machine code, basically assembly language, and trying to do this, ending up sort of simplifying the dynamics of all these balls bouncing around to some kind of just a bunch of bits on a grid. And, well, it was a disappointment because it didn't work. It didn't show the same picture as was on the cover of the book. So I was like, okay, that didn't work. I went off and worked on particle physics and cosmology and a bunch of other things and started building computer languages and so on. And then kind of many years later, I came back to this question and I realized that actually it had worked, I think. Unfortunately, I'm not sure I have the program anymore. I have some paper tapes that I used on that machine, but it's not really that easy to read a paper tape anymore. And worse than that, I wrote a paper tape loader, which is the actual encoding thing that encodes the way that the paper tape works. I don't have the code of my loader anymore, and so that gives an even greater level of difficulty in figuring out what's going on. But in any case,
I think I saw you fix that simulation, at least because I saw in I don't remember if it was one of your books or articles where if you take that like square block and you're using like square molecules and you just add like a little bit of nudges or offsets or things like that, then you get the behavior that one would expect.
Yes.
It's kind of entropic mixing, right?
Yeah, actually, the thing that I think I did back when I was using that paper tape computer was even more like a cellular automaton, like something where there's just a grid of positions rather than having continuous positions. But yes, absolutely. At this point, now I understand how this all works. But when I was 12, 13 years old, I didn't.
Before we get, because you said some really interesting things, and before we get too far from the irreversibility aspect, I'd like to pick your brain on that, because
Sure.
This has been one of the most enduring mysteries, right, of modern physics, is that all our laws are reversible, and yet the behavior that we observe in the universe is manifestly irreversible.
Yep.
And I guess there's been kind of two solutions to that. One is to say, well, maybe there is some intrinsic irreversibility in the laws, right, that in the time evolution, this sort of thing. That's one possibility. Another is that long ago, the Big Bang in the distant past was just very special. It was this ultra low entropy state, and therefore that's why we have this apparent motion, if you will, dynamics away from this low entropy to a high entropy. So I'm curious, in kind of your physics project in the Rullial space and the evolution that you imagine on the hypergraph, which is it? Is it that the distant past was unique, or that the laws are irreversible themselves?
Oh boy, that's complicated. Okay, so there are several different things going on. Okay, and but the most immediate one is the following thing. Essentially, what's happening in just gas molecules. Let's forget the early universe for a second. We're going to come back to the early universe because it's very interesting. But just gas molecules bouncing around in a box. The thing that I think the right way to think about it is it's like encryption. you have these initial conditions. They can be quite special, but when these gas molecules bounce around, they're effectively doing a computation to work out where the gas molecules will end up. That computation we can think of as like an encryption of the initial conditions. The data about the initial conditions is still absolutely there. There's still reversibility. If we did the computation backwards, we would get those initial conditions. So why is it that we don't notice that? Well, the problem is because the positions of the gas molecules in effect have been encrypted. And so when we look at the output, if we're not great cryptanalysts, we can't see that inversion. When we just come and we measure it and we just have our simple ways of measuring things, it just looks random to us. We're not able to do the cryptanalysis to see how to go backwards.
What's the problem?
So I think the essential phenomenon is this interplay between the computational process, what I call computational irreducibility of the actual dynamics of the molecules, coupled with the computational boundedness of our ability to observe things. So when we make observations, we're always taking lots of detail and we're aggregating it together. Like when we look out at, the scene that I'm looking at right now, there are lots of photons falling on the retina of my eye. There's lots of nerve impulses, but in the end, I'm looking at a camera. That's the thing my brain is thinking. I'm taking all that detail and I'm kind of aggregating it down to this one fact that I'm looking at this camera. And by the way, I'm not working out every individual pixel and doing this very complicated computation on them. I'm just averaging them in some simple way. And so, I think the core of the second law is this interplay between the underlying computational process, which is kind of like doing this encryption, and the way that we observe it, which is we are limited in our ability. Our minds are and our sensory apparatus and our measuring devices are limited in their sort of computational ability. They can't follow every individual molecule. They can't do that cryptanalysis to find out where it came from. Now, when I talk about sort of the dynamics of the system encrypting its initial conditions, the way we have to think about it is the process of physical process of molecules bouncing around and so on, that's like a computation. Now the question is it like a computation where we can just jump ahead and say, and the answer is 42, or is it a computation where the only way we can know the answer is by doing every step in the computation? And one of the things that I discovered in the 1980s and have sort of built a lot on top of is this idea of computation.
I don't know, man. This guy hasn't said anything interesting so far, and they're really hyping him up. I am very I don't know. I don't know if it's a real thing or they're just hyping him up. We'll see. He has said some personal opinion about entropy. Don't know.
Irreducibility.
See,
that there are many computations, even ones specified by incredibly tiny programs, which have this feature that you really can't reduce them. You can't jump ahead and say, and the answer is going to be this. You're really just stuck going through every step of the computation. In fact, this phenomenon of computational irreducibility is, I think, one that is sort of a tremendously important sort of piece of science and intuition, because it's the thing that kind of tells you science isn't going to be able to give you all the answers. Science, as what we have thought about in terms of it's just this thing where we feed in the input and we immediately make a prediction, that's not going to work. That has many implications for AI, for example. If you say, I'm going to set up the rules for my AI and I'm going to get them just right so that I can know that my AI is never going to do the wrong thing. Okay, computational irreducibility says it's just not going to work. You're just never going to know. There are always going to be things where...
What's he saying?
To know what it's going to do, you have to just run it and see what it does. And so that phenomenon of computational irreducibility, that's what happens with gas molecules. And it's our inability to sort of do all that elaborate computation that means that we perceive what's happening to be, you start off with these very orderly gas molecules, but you end up with something that looks random, at least to us, at least to the computationally bounded us. Now, when I mean, so that's, I think, the core of what's going on. It's this process of sort of computational irreducibility underneath, and our sort of limited computational abilities kind of at the top. Now, you know, I will say that I mean, this is, gosh, this gets quite deep quite quickly, but one of the things, okay, so in 20th century physics, there were sort of three big theories: general relativity, theory of space-time, quantum mechanics, and statistical mechanics, the theory of what happens with lots of molecules and so on. And the sort of the key result of statistical mechanics is the second law of thermodynamics. And what people had thought in the 1800s was, well, statistical mechanics and the...
Honestly, they call him the greatest scientist alive, and just saying a bunch of nonsense.
second law in particular, we're going to be able to derive that from sort of the mechanics of molecules. There's just going to be some way in which the mechanics of molecules inevitably leads to the second law. But they didn't think that general relativity would be of that character, nor did they think quantum mechanics would be of that character. They thought those things would be things that were just, well, the universe happens to be set up that way. We don't get to derive those kinds of things. The thing that, for me, is just, I'm really excited about, is that I think we now understand that all three of those theories are in the same sense derivable, and they all come from the same phenomenon, which to me is just, well, if you're in the physics business, I think that's spectacular. It's the phenomenon of the interplay between computational irreducibility of underlying processes and our feature as observers. The fact that we are observers that are the way we are, with our kind of computationally bounded abilities and so on, that happens to be the way we are. We could imagine the aliens, so to speak, who work differently, but we work this way. And so the thing that we then discover is, in the case of space-time, what we now think is that the universe at a sufficiently small scale is made of discrete atoms of space that are related by this kind of hypergraph. And as sort of the process, time is the process of the progressive rewriting of that hypergraph. Time is the computational process. The passage of time is the execution of the computation that is those pieces of the hypergraph getting rewritten. But we don't perceive space as a bunch of atoms of space in hypergraph. We perceive continuum space. The fact that we perceive continuum space is because we are making a sort of computationally bounded observation. We are averaging out all those particular points of view about how the universe works. And so I sort of realize
Unbelievable. Like, absolutely.
I don't know whether it's really true, but I don't know whether there's a correspondence between...
How to refuel your fuel tank and be less ADHD. Busted. Carbon capture busted. Let's watch that. Bigfoot.
And CO2 can be extracted from the atmosphere and stored underground to create negative emissions and reduce the CO2 content of the atmosphere.
So this is our prototype air contactor. This is the smallest module of what will eventually be multiplied up many times to form our full-scale system.
Air capture absorbs carbon dioxide that's already been emitted. This seems to be one of the only feasible ways of trapping emissions from small mobile sources like cars, trucks, and planes.
Here at Carbon Engineering, we are developing technologies to take carbon dioxide directly out of the atmosphere. With the appropriate design and the right scale, we can start today.
Nope, it's all financially dead on arrival. It's all greenwashing vaporware, and it's trivial to prove as such. So it all boils down to this. This is essentially gasoline. It is the absolute king of cheap, safe energy density. There is a very good reason why we use almost exactly the same stuff to run our cars today as we did 100 years ago, because the chemistry has been well understood for over 100 years. Nothing is going to beat this in terms of energy density. It's just a teensy tiny problem. When you burn this, it releases carbon dioxide, which heats up the planet. So it really doesn't matter which one of the hydrocarbons you're burning, whether it's butane or hexane or octane or body fat. They're all essentially the same chemically. They're all hydrocarbon. So how much carbon dioxide you're going to get from burning a kilo of any of these? And for reference, this is about a kilo. So the proportions here are about right. You burn about a litre of gasoline, you're going to end up with about a litre of carbon dioxide. It's basically 1-to-1 in terms of volume. Now, in terms of density, of course, gasoline is significantly less dense than this stuff. So it's about a kilo of this gives about 2-3 kilos carbon dioxide, that sort of thing. But in terms of volume, it's basically 1-to-1. So it's dead easy then. For every kilo or so gasoline that you burn, you have to take a couple of kilos of carbon dioxide out of the atom.
I don't like that. Let's see. How GPS works and how it got better than the designer ever imagined. Let's watch that. Sure, why not?
Hello, it's Scott Manley here. As you may have heard, I'm a bit of a fan of space and spaceflight. You know, when I meet regular people on the street, I like to talk to them about space and spaceflight, and they think, well, that's all very interesting, but they say, I don't have to worry about this stuff in my everyday life. I mean, you don't exactly have to do orbital mechanics to figure out, say, how to get to work. At least that's what they think, because if you're using a phone to navigate, it is using GPS, and for GPS to work, the receiver has to figure out the orbits of the satellites that it's receiving from. So effectively, all navigation we do these days is orbital navigation. You see, GPS has become a core part of technology. Initially, when GPS came along, it was like low precision. It was actually thought that civilian GPS would have a precision of 100 meters. It was more like 30 to 50 meters, but nowadays it is accurate enough that it is possible to land an aircraft on autopilot, right? I've been flying around in aircraft and I see GPS is everywhere. Like when I fly my service, you might have seen some videos from it, and the display in front of me, the primary flight display, displays a 3D model of the terrain, and that's used GPS and orientation data to show what I should be seeing if I was, say, inside a cloud. And, you know, you can see that this is accurate enough that when I come down to the runway, it's putting me in exactly the right position. Also, you know, like every instrument approach, a lot of the instrument approaches these days are all GPS based, and every aircraft flying around is using ADS-B instead of secondary radar for their locations. As I said, it's everywhere. So how did we go from something of this very low precision to something that was so precise? Well, that's what we're going to talk about today, right? So GPS was conceived at the Pentagon over Labor Day weekend in 1973. So this is like the 50th anniversary purely by accident. Yeah, it was back then, it was called Defense Navigation Satellite System, DNSS, and they took their inspiration from a couple of projects that already existed. There was the Navy's Timation system, which had high precision clocks on satellites that would just orbit in low orbit, and they would beam the time down to military ships or Navy ships so it could be used for other navigation systems, either tracking against the stars or maybe talking to the LORAN system. And there was another project that was an abandoned idea for satellite-based navigation called Project 621B. So out of this meeting came the basic idea for GPS, where you had 26 satellites in 12-hour orbits, you know, high up. They could see a lot of the surface. So the first GPS satellite was launched in 1978. By 1993, the network was fully operational. And in the intervening years, there were two very important events that sort of shaped GPS in the early years. First, there was the incident with Korea Airlines Flight 007, which on flying from Alaska to Seoul, made a navigational error with the autopilot and flew over Soviet airspace and was shot down with the loss of everyone on board. And as a result of that, Ronald Reagan essentially signed an order saying that the GPS system, although it had been intended for the military, would have a civilian component available to everyone to avoid these things going forwards. And then 1990, the first Gulf War. At that point, the US military still hadn't been totally sold on GPS capabilities. But the people on the ground, they were finding that these GPS receivers that they had acquired for marine work or for on boats, these were perfect for navigating the featureless landscapes of Iraq out in the desert storm. And so families back in the US were purchasing these things and getting them shipped to their people on the ground to help them out with their navigation needs. And of course that then accelerated the armed forces adoption of GPS, and nowadays we have an incredibly it's a pervasive system that is everywhere, right? So the basic way that the global positioning system works, as many of you probably know, is that you have a number of satellites in these high orbits, and they are transmitting signals with very accurate clock codes. And by reading these signals, you can get a measurement of the distance to the satellite, and by knowing the orbits of the satellite, you can figure out where you are on the surface. And you might think, well, okay, I'm trying to get my position in three-dimensional space, so I need 3 satellites. Not quite, because the satellites have these incredibly accurate, incredibly expensive clocks, and they wanted a system which didn't require incredibly accurate and incredibly expensive clocks on the ground. So what you have is a not quite as good clock, and that means you can't really accurately measure the distance to the satellite, but you can measure the differences in arrival times from these signals and use that to figure out roughly how accurate your clock is. So what you're really measuring is a 4-dimensional value, your X, Y, Z, and your delta T time correction. That means you need a minimum 4 satellites for GPS to work. Now, the system they initially launched used 2 different frequencies. It used the L1 frequency, which was 1575.42 megahertz, and then there was the L2 frequency at 122.7.6 megahertz. And more modern satellites also have the L5 signal, and we'll talk about that. Now, the initial satellites had the standard positioning system, which was provided by the coarse acquisition code on the L1 frequency. And then it had the precise positioning system used by the military, and that used the code on L1 and L2. So the way this worked was it used CDMA, right? What is CDMA? Well, GPS was actually one of the first systems to actually use this. So CDMA stands for Code Division Multiple Access. If you're like tuning your car radio to different frequencies, that is frequency division, right? You're using a separate frequency for each transmitter. There's another, TDMA is time division, so that's where you have a series of things cooperating on the same frequency and they all choose to transmit at different times and they coordinate amongst themselves. CDMA is Code Division Multiple Access, and this is where it gets cool. So what you have is a binary code, and in the case of what's called the coarse acquisition signal, you have a 1023-bit sequence, which is unique to each satellite. There's up to 32 different codes. And what you do is you take the signal and you essentially convolve it, we multiply it by the signal that's coming in. And if you get the things lined up to within 1 bit, you will see a very strong correlated signal. And if you're not quite there, you'll have a weak, less than 10% correlated signal. So once you get these things lined up, you multiply them out and you can start to extract the actual underlying bit. So this code is just a way of finding the signal and identifying the specific signal. And the beautiful thing is you can have 2 or 3 different satellites broadcasting on the same band. You could have like dozens of satellites on the same band. And while they're talking all over each other, by multiplying it by this code, you basically extract out the specific frequency or the specific data for that satellite. And that's how code division works. So with the geostation, the GPS satellites, the code is transmitted 1,000 times a second. 1023-bit sequence is transmitted 1,000 times a second, right? And that in turn encodes a 50-bit per second data signal. So you have like 20 repetitions of the 1023-bit sequence, and then the bit may flip or not, and you have like 50 bits per second. Each data frame is like 300 bits, and it takes 5 data frames to transmit a whole sequence. So you have a 30-second block of data that is being transmitted on the coarse acquisition frequency. And what this contains is synchronization words to actually make sure that you're actually synchronized with the underlying data stream. The timing of each frame. It contains the orbital parameters for the satellite in question. It also then contains parameters for correcting for things like ionosphere and solar weather. And finally, it will contain in each 30-second block orbital parameters for at least one other satellite, not at least. And so it iterates through all the other satellites, and over 12.5 minutes, it will transmit the positions or the orbital elements of all the other satellites. And that's called startup. So it takes about 12.5 minutes to fully warm up a GPS receiver. But once it's warmed up, it can store that stuff in memory and predict forward. So the next time it turns on, it knows what satellites it thinks it should be able to see, and therefore can quickly bootstrap into this, try the relevant code and synchronize them, and hopefully get started a whole lot faster. So anyway, that's roughly how this works. I would like to go into a whole lot more detail, but frankly, that is like a task for somebody that wants to talk about your software-defined radio. So anyway, coming back, you have this sequence, so you're transmitting about 1,000 bits, or chips as they're called, per second, and you're transmitting these time signatures, so you can tell exactly on the bit boundary what time things are. So you can imagine if the speed of light is 300,000 kilometers per second, then 1 million samples per second should get you about 300 meter accuracy. But actually hardware can go better than that, because they can actually measure the transitions between bits and get the position estimate down to, like 30 meters or thereabouts. Now, the military code, it's also transmitted at the same time, but the military code doesn't repeat the same 1024 bits in sequence. It has for each satellite, it has a week-long sequence. And what you do is you sort of tune in, you synchronize using the coarse acquisition code, which will let you know what time it is. And then from that code, you can then figure out where you are in the big long week sequence and then synchronize to that. And now you're in on the military channel, and the military channels use 10 times the bit rate, so they can get shorter, more accurate measurements. But more importantly, they also work on 2 different frequencies, the L1 and the L2. And by having 2 different frequencies, you can compensate for one very important source of error, the delay due to the ionosphere. So the ionosphere is up above the atmosphere. It's a region where you have free electrons that have been pushed, kicked off their atoms by things like cosmic rays, and more importantly, ultraviolet light from the sun. And these electrons and protons floating around, they interact with the radio waves and slow them down a little. So because of the ionospheric delay, that translates to a delay in the signal equivalent to about 10 to 20 meters. So you lose about 10 to 20 meters of accuracy just because of ionospheric delay. And as I said, the basic civilian signal that's transmitted includes a model of the ionosphere, which is specific to that time, and so it changes over time. They can update it. And so they can cut that error in half using this very model. But the military system, because it has 2 different frequencies, and because the effect of the ionosphere is dispersive, that is, it affects different frequencies by different amounts, you can look at the differences between the L1 and the L2 frequencies and compute the actual electron density, and therefore what the actual delay should be, and almost remove it entirely just by using the 2 different frequencies. So, yeah, the military signal was a lot more accurate. Originally, the US, when they designed it, they thought that they would have 100-meter precision for the civilian system, and that was what they wanted it to be kept at. The problem was then that people that looked at the signal and worked with their, smart human brains on it, they were able to get higher and higher precision. So, a another system had been designed into GPS to make it less accurate for civilians. It was a feature called selective availability, and that's where they would introduce very subtle clock delays. The clocks on the satellites would wobble back and forth by less than a microsecond. And they would do this in a way that could be calculated by the military side, but not by the civilians. And so that meant that when selective availability was turned on, the civilian gear would vary its location by about 50 to 100 meters. And this is what the military wanted, but it turned out that the US government is not a monolithic entity, and there were other agencies that really wanted to use this global positioning system. There was the US Coast Guard, the Department of Transport, the FAA. They all wanted better precision for their particular things, and even though the Department of Defense and these guys were all on Team USA, they couldn't get special treatment. So they had to come up with their own solutions independent of the Department of Defense. The US Coast Guard wanted really accurate navigation data to help shipping around the coast, and so they came up with something called differential GPS. I mean, they didn't invent it, but they began to deploy it. The idea with differential GPS is that you have receivers that are placed at known points where you know the precision to within millimeters, and they then take the GPS signals, they measure them, and they compare their solution to what it should be, and by then subtracting that error and telling everyone around them, they can say, well, I'm measuring 10 meters east of where I really am, so everybody nearby them says, well, I will adjust my position by 10 meters to the east so that I'm actually in the correct location. And this was great. This meant that they could get resolution of a few meters, and that allowed the US Coast Guard to work with shipping and to transmit correction data to ships that were working in and around the US. Now, it wasn't just the US Coast Guard that did this. Countries all over the world took GPS and they built their own differential GPS systems. I mean, the difference is that the US, the US Coast Guard would obviously go to, a US government Thanksgiving dinner and be all passive-aggressive towards the Department of Defense. Where's my precision? Come on. So the fact that the US government was sort of competing against itself on this GPS precision thing wasn't lost on the higher-ups in the US government. And in May of 2000, they turned off selective availability forever. And there's actually great graphs showing the drop or the increase in the precision exactly at 4 a.m. on May 2nd or whatever. It's also interesting, if you look at this graph, you can see the horizontal error and the vertical error are separate on these. And if you look carefully, you'll see that the vertical error, the error in your altitude, is about twice as much as the horizontal error. And this is important. The reason why this happens is, if you think about it, you want to have the widest range of directions so that you can get best precision, right? If you have everything all in one direction, then you've got you've got a lot of errors. But if you have things at almost opposite sides of the sky, that's almost the best condition. However, while you can have satellites to the north, the south, to the east, and the west, you can't have satellites up and down because the ones below you can't be seen. So you have only half the space to work with in the vertical axis. Therefore, you have half the precision in the vertical axis. So that vertical error was very important for one other government agency, the FAA. They wanted to revolutionize aerial navigation using GPS, and GPS was not accurate enough for them. Again, the original spec said 100 meters, and that was definitely not good, especially when you consider the vertical differences would be even larger. So the FAA were working on their own differential GPS solution, but instead of transmitting the augmentation, directly to the aircraft via ground-based antenna, they wanted to send everything up to satellites in geostationary orbit and then have those send down to the aircraft using pretty much the same protocols that GPS systems actually used. So this is what's called a satellite-based augmentation system. You use geostationary satellites, and these aren't US government geostationary satellites. These are just commercial GEO satellites, and US, Federal Aviation, they buy like some bandwidth on it, they put in their software, and then they're just basically transmitting this data down in a format that is usable by aircraft. So it's called the Wide Area Augmentation System, or WAAS, and it is pretty much required on any new aircraft. In fact, indeed, many old aircraft have it now, despite it being a very kind of new system. It was originally deployed in 2003, and as of 2020, I think it was pretty much required in every aircraft that operates in the major airspaces in the US. So if you want to fly within 30 miles of a Class Bravo, that is something like San Francisco Airport, then you have to have ADS-B, which requires a WAAS-capable GPS system. Now, Europe has a similar requirement. They have their own network. It's called EGNOS, the European Geostationary Navigation Overlay Service, and it literally is the same technology using practically the same protocols, to the extent that the same hardware on the aircraft can talk to both systems and interoperate correctly. So the goal of the FAA was to get the precision down to about 7.5 meters of accuracy. But actually, they did way better. It turns out that measured performance is about 1 meter precision at the 95th percentile. And the other thing about this whole WAAS system is that it doesn't just augment the quality, the accuracy of the satellite. They can also detect when there is a misbehaving satellite and instantly tell all the aircraft to start ignoring this particular satellite. And this happens. There are cases where satellites were moved on orbit and they weren't taken out of the network, and so aircraft that were using this satellite suddenly found their positions drifting by about 100 meters, which would be really bad if you were, say, on a very narrow approach into one of these mountain airfields and you couldn't see where you were going. When you're flying with instrument rules, you need all the precision you can get. And these days, if you look at the majority of instrument procedures, they are all now coming up with GPS-based procedures because they work, they are more diverse. A lot of the old navigation hardware, like VORs and non-directional beacons and DME, these old ground-based systems are either being disabled, or they're being shut down, or they're failing and nobody's wanting to repair them because they're not essential. And so over time, we've not only added a whole bunch of GPS-based approaches to airfields which would never have them, but we've also got rid of a lot of the old hardware, and this is starting to dominate. One of the important things to realize about these differential GPS systems is that the accuracy enhancement falls off as you get further and further from the ground station, because there's just differences in the strength of the ionosphere over time, over distance. So there's another thing they have is like a local augmentation system, where you have a specific airport with a specific receiver, and then that can transmit updates locally to those aircraft, and then they can get, again, this sub-meter precision using GPS with the local augmentation. And that's great if you want to get very accurate approach vectors for any runway. Just say you have 2 or 3, 4, 5 runways, and you don't want to have to build instrument landing system antennas for all of them. You just put in one GPS, augmentation system, and boom, you've got the ability to define approaches for all of these things and get your aircraft landed. You can even define approaches which would never have been possible using the previous gear. So, the success of this WAAS system means that the terrestrial network that had been developed by the Coast Guard was no longer being needed anymore. So it was actually shut down in 2020, and now even the marine shipping is able to use these area augmentation systems. And now the GPS satellites themselves, those are also undergoing improvements, modernization of the protocols. So back in 2005, we got the first modern satellite that was launched. There was a Block 2R-M, and this started transmitting new civilian signals. It was called the L1C and the L2C. And that meant that we had a civilian signal on the L1 and the L2 frequencies, so you could do those direct ionospheric measurement. They also added the L5 frequency. Right, this is another frequency range. It was down in a range of frequencies which were supposed to be for aviation navigation, so this fit right in. It transmits at higher power, there's more resolution in the signal, and that means there's less problems with interference, right? Also, new data formats. So the L1C, it transmits on the same frequency as the coarse acquisition. And the thing is, they didn't want to just shut down the old coarse acquisition system, so they kept that running. What you have is the new civilian signal is still transmitting. It's using different codes, different code sequences. So by CDMA, you can still pull this out. But there's a neat trick that they did by carefully choosing their sequence. They can shift like the spectral power around the center of the frequency so that the original one had this like big peak in the middle, and then you have a minima and these lobes that come out. Well, they changed the bit sequence in a very subtle way to make it wiggle more, and now instead of having a big peak in the middle, they've got nothing in the middle and the lobe comes up. And so if you look at these two things on top of each other, the two different civilian signals, the old one and the new one, the old one is strong in one place, and where the old one is weak, this new one is strong. So they're complementing each other, literally fitting the bits into the gaps in the spectrum just by very carefully doing the math on their Fourier series. It's very clever. And, they do the same thing with the military signal. The new military signal pushes a lot of the energy far out into the lobes, which actually then apparently makes it harder to jam, because if you jam the middle of the frequency, sure, you take out the old GPS, but the military one is sitting far out on the sides, and it's sort of just working just fine while everybody else's GPS stuff isn't working. It's all very clever stuff, and I wish I totally understood it. Now, I should probably finish as well by saying that GPS isn't the only game in town. When we're talking about global navigation satellite systems, there's at least 3 other major players. There's GLONASS, which is the Soviet, which became a Russian system. There's the European Galileo, and the Chinese Beidou. And they're all actually pretty close in the design. They all have their bands very close to each other. The formats are largely software differences. And one thing is significantly different is that the old GLONASS actually uses different frequencies for the satellites. And I think it's interesting because I think they have 8 frequencies available, and they have 16 satellites. So the way they fix this is they make sure that the same frequency is assigned to satellites that are on the opposite side of the Earth from each other, so they will never interfere. So they have these pairs that are opposing and on the same frequency. But yeah, other than that, all these different networks, they all, talking to them is largely a software change, and that's important if you're, say, building the aviation, the GPS systems, the navigation systems for aircraft, because it's literally a software tweak to switch from one to the other and to transparently move from one country to another and provide consistent navigation so that you can make these accurate approaches and landings. I'm Scott Manley. Fly safe.
Alright, let's see what else we got here. The unreasonable effectiveness of atomic layer deposition.
episode of the Y-Files is brought to you by PDS Debt. For thousands of years, the world has been captivated by the mystery of Atlantis. The concept of an ancient city hidden beneath the ocean is intriguing. But what if there was not just a city, but an entire continent buried beneath the waves? The continent of Lemuria is a huge landmass believed to have sunk in the Indian Ocean after some ancient catastrophic event. Atlantis and Lemuria are similar in that they've sparked numerous theories, legends, and interpretations. But Atlantis and Lemuria are very different in one way. There's no proof of Atlantis.
Alright, let's let me bring this up.
Interpretations. But Atlantis and Lemuria are very different in one way. There's no proof of Atlantis. No, don't put them anywhere. I didn't order 40 palm trees. I don't care where you put them, just don't leave them at my house. I can't hear you. What are you saying?
Hang on. Hey, Mary, close the door, would you? And tell the boys to take 5. Don't play the union card with me, Mary. You'll still get paid for the break. Sheesh, contractors, am I right?
Contractors? What are you working on?
Oh, this? We're working on the terrarium today.
Terrarium?
Yeah, it's a type of enclosure for plants and animals.
I know what a terrarium is. What does this have to do with me?
Well, the boys are working on the footings for the camel box and the terrarium. And I'm a little light on funds, so I need you to do a little teeny tiny, weeny baby teeny tiny money transfer so that I can pay the framers and order the sand.
Okay, I understand the words you're saying, but none of this makes any sense.
Oy vey, we are building out the base for the dune, which I have named the camel box, which is in the new terrarium. And I need to pay these guys and put in the order for the 35 cubic yards of sand.
35 cubic yards? How much sand is that?
About 50 tons, depending on the size of the grain. Look, can you do the transfer, please? I don't have time to educate you on sand dunes, and these guys are still on the clock. Besides, I don't need the teamsters on my dorsal fin, you know what I'm talking about?
Again, I understood the words, but did you say 50 tons of sand?
Yeah, it might be a little less depending on the size of the oasis I put in. And what palapa I get.
Palapa?
Yeah, it's a type of beach hut.
I know what a palapa is. What is going on?
I told you that Gertie was feeling homesick, and I wanted to do something to cheer her up. And you said that I could. So I'm building a terrarium in the backyard for her. It's gonna have sand dunes and an oasis with a palapa. Excuse me. And an oasis with a beach hut.
Again, I don't know what
and
this...
I need you to float me a few shekels temporarily so they can get this thing finished.
Yeah, but I thought you were gonna cheer her up with some hay or some flowers. Did you say backyard? You don't have a backyard. I have a backyard.
But the work has already started. The bank said I have too many monthly payments for a construction loan. Have you ever seen a depressed camel?
I don't think it's...
Gertie's hump is sagging to one side, and now she's listing to the left. She's just walking around in circles like my uncle lost his left fin in Nam. Oh, it's painful to watch.
Okay, just slow down. Will you call PDS Debt? They have options available for people struggling with monthly debt payments. Credit cards, collections, medical bills, personal loans.
Ooh, you smell that?
What?
That smells like today's sponsor.
Yep. If you're making monthly payments every month and your balances aren't going down, PDS can help. They roll your debt into one low 0% interest monthly payment. You can save thousands in interest and fees and pay off your debt in a fraction of the time.
Yeah, but I have a lot of debt. But it's
qualified you. Stop this.
Alright, let's see.
In 1858, zoologist Philip Sclater made a name for himself in the scientific community. He divided the world into 6 geographic regions based on the distribution of animal species. They were Palearctic, Ethiopian, Indian, Australasian, Nearctic, and Neotropical. Sclater's system is still used today. While Sclater created his classification system, a mystery emerged: the fossils of lemurs. Lemur fossils were found in parts of South America, India, Africa, and Madagascar. These areas are not connected by land, but lemurs don't swim. The question haunted Sclater: how did lemurs spread across the world? Identical species don't develop in different places at once. He had a radical answer: that there was a landmass once connecting these areas. It would need to be massive, bigger than Australia. His theory was a stretch, but it would solve the mysteries he'd stumbled upon. Along with the unexplainable locations of lemurs, Sclater also uncovered extreme similarities between monkeys found in South America and Africa. In 1864, Sclater published an essay about his theory in a scientific journal. In the essay, he refers to his proposed continent as Lemuria.
Anterior to the existence of Africa in its present shape, a large continent occupied parts of the Atlantic and Indian Oceans, stretching out towards what is now America to the west and to India on the east. In Madagascar and the Mascarene Islands, we have existing relics of this great continent, for which, as the original focus of the Stirps Lemurum, I should propose the name Lemuria.
This land bridge concept was popular in the scientific community at the time. Sir Charles Lyell, a well-known geologist and teacher, believed continents were rising above and sinking below the ocean routinely, just very gradually. So it's no surprise that following the publication of Philip Sclater's essay, the Lemuria theory really caught on. It turned out Lemuria may have been the answer to many scientific mysteries. In fact, Lemuria may have been the birthplace of humanity itself. In 1864, Philip Sclater introduced the concept of Lemuria to the world. 24 years later, Helena Blavatsky, a Russian theosophist and co-founder of the Theosophical Society, published a book titled The Secret Doctrine. Theosophists, like Blavatsky, are truth seekers who study a combination of religion, science, and philosophy. They believe in an ancient wisdom that unites all major religions. The Secret Doctrine discusses the origins of humanity. It outlines a sequence of 7 root races representing different stages of human development. Currently, we are in the 5th stage, with the 6th and 7th yet to come. According to the Secret Doctrine and other writings by Blavatsky's followers, the first root race was ethereal and didn't possess physical bodies. They may have appeared as giant phantoms. The second root race was shapeless and asexual.
Asexual?
Well, they didn't engage in sexual activity.
Sounds like they were married.
They reproduced through a process called budding, which is essentially natural cloning. The third root race thrived in Lemuria and coexisted with dinosaurs. According to Theosophist W. Scott Elliott, these Lemurians were giants.
His stature was gigantic, somewhere between 12 and 15 feet. His skin was of a yellowish-brown color. He had a strangely flattened face, eyes small but piercing, and set curiously far apart, so that he could see sideways as well as in front. The head sloped backwards and upwards in a rather curious way. The arms and legs, especially the former, were longer in proportion than ours.
Early in the Lemurian period, these supposed human ancestors laid eggs, but over millions of years, their reproductive process developed into, well, the one that we know today.
That process has gotten me in a lot of trouble over the years.
Well, maybe you shouldn't have engaged in the process as much as you did.
Yeah, what can I tell you? The ladies love me.
But Blavatsky and her followers weren't the only people who wrote about the Lemurians. A few years later, British writer James Churchward started writing about the sunken continent of Mu. At first, Mu was thought to be the inspiration for Plato's story of Atlantis, but Churchward connected it to Lemuria, and now many consider these lost continents one and the same. James Churchward's work is based on the translations of ancient Indian tablets. These texts are included in a series of books called The Children of Mu. The tablets describe an ancient civilization of 60 million people that was eventually destroyed. According to Churchward and others like archaeologist Augustus Lake-Langevin, the sunken continent of Mu once stretched from Hawaii in the north to Easter Island in the east and almost reached Japan in the west. The Yonaguni Monument off the coast of Japan is believed to be the underwater ruins of this lost civilization. Nam Madal in Micronesia is considered the southern part of Mu. The site contains structures made of large volcanic rock logs. It's unknown who built them or how, but the society was advanced. Recent LiDAR imaging revealed an artificial irrigation system that provided fresh water to residents throughout the area. They even had a sewer system, years before the ancient Greeks or other advanced civilizations. Easter Island marks the eastern point of Mu. Take a look at Easter Island. It's a small island in the middle of nowhere, yet it was once home to 12,000 people. How did they get there? Mainstream science says they traveled thousands of miles across the Pacific Ocean in canoes. But if the continent of Mu existed, they could have just walked there. This could also explain the similarities between Polynesian languages and Greek, as well as the worship of a sun god named Ra on Easter Island, which is similar to the Egyptian sun god Ra. These similarities of language and religion suggest that these cultures either intermingled or originated from a common source. James Churchward, Le Plongeon, Helena Blavatsky, they all describe Lemuria and Mu differently, but there's one thing they all agree on. It was destroyed in a terrible cataclysm. Chan Thomas, in his book The Adam and Eve Story, presents compelling evidence that global disasters occur in a cycle. Lemuria might have been destroyed during one of these events. According to James Bramwell and William Scott Elliott, supporters of this theory, Lemuria was destroyed 11,500 years ago in a global disaster. And evidence of a global cataclysm can be found all over the earth, from the pyramids of Giza, across Africa, and even on Easter Island. Now, of course, I'm referring to the Great Flood mentioned in the myths of every culture on Earth. The flood that occurred during a period of history called the Young Dryas. As the last ice age drew to a close, the massive ice sheets that had covered much of the northern hemisphere began to rapidly melt away. Great torrents of fresh water poured into the oceans, causing sea levels to rise dramatically across the globe.
Hey, maybe instead of Younger Dryas, it should be called a Younger Wet Ass. What?
Coastal areas were transformed by the flood as shorelines expanded inland by hundreds of miles. Entire land masses were submerged beneath the rising seas. The lives of every human on Earth were disrupted by the Great Flood. Entire cultures that had been tied to the old shorelines were shattered and scattered. But a few resourceful people survived and rebuilt their civilization. But this time they did it in secret and hidden far away from any future global catastrophe. But what caused the ice sheets to melt in the first place? There's disagreement about this. Some think it was the impact of a massive comet or asteroid. Others think it was a solar event so destructive that plasma from the sun stripped away the Earth's magnetic field, exposing the planet to extreme heat and radiation. Or a pole shift, which would also create a worldwide disaster. But there is one legend of Lemuria that contains a different explanation. That the Great Flood wasn't caused by an asteroid or the sun. It's said that the Great Flood was caused by people. According to Blavatsky, Lemuria was destroyed by fire. Volcanic eruptions shattered the continent into islands. Slowly the islands sank into the sea, along with Lemurian history. James Churchward's version of the sinking of Mu is more dramatic and immediate. The civilization was obliterated in a single night of terror. Intense earthquakes shook the land. Volcanic eruptions spewed fire and ash. Relentless tsunamis engulfed the entire continent. It was a catastrophic event. In one night, everything was gone. There are even speculations that the Lemurians were eradicated by a pole shift, a sudden and civilization-ending event. Churchward's depiction resembles this cataclysmic shift. Volcanoes erupting around the world simultaneously, massive waves flooding everything, an entire civilization wiped away in an afternoon. Others propose something even more chilling. The destruction of Lemuria was not natural at all. They believe it was intentional. There is a 10,000-year-old story, which appears in books like the Chronicles of Akakor, which says the lost continents of Lemuria and Atlantis sank due to a nuclear war caused by the Anunnaki. The Anunnaki are deities of the ancient Sumerians, Akkadians, Assyrians, and Babylonians. And some consider the Anunnaki an alien race who created humans through DNA manipulation, then used humans as slaves.
Facts.
A full Anunnaki episode is coming up.
Oh, how you tease.
The Chronicles of Akakor tells the story of two hostile divine races that eventually went to war.
The four corners of the earth were red. The two races of gods started to dispute.
In J.J. Benitez's book, The Visitors, he recounts the alien abduction of a scientist, Daniel W. Fry, on July 4th, 1959. While Fry was on the alien vessel, they told him that they were the descendants of a race who lived on the land of Mu. They said there was another advanced civilization on Earth that we call the Atlanteans. Edgar Casey also received telepathic messages about Atlantis. He described their culture and their technology.
In our great city, we harnessed the Firestone's energy through advanced mechanics. Our domed power station concentrated the stone's rays via prisms. This energy propelled our crafts through induction. similar to your remote radio control. Though invisible, the rays powered vehicles through the air on land and sea. Carefully aligned, the stone's forces regenerated human bodies and fueled industries.
Casey also predicted that Atlantis would eventually be discovered.
The position as the continent Atlantis occupied is that as between the Gulf of Mexico on the one hand and the Mediterranean upon the other. Evidences of this lost civilization are to be found in the Pyrenees and Morocco on the one hand, British Honduras, Yucatan and America upon the other, the British West Indies or the Bahamas, and a portion of same that may be seen in the present, if the geological survey would be made in some of these, especially or notably in Bimini and in the Gulf Stream through this vicinity. These may be even yet determined.
Now keep in mind that it was 1939 when Edgar Casey predicted that Atlanta would be discovered in Bimini in the Bahamas. The Bimini Road wasn't discovered until 1968. According to Casey and others, Atlanteans lived peacefully on Earth for over 200,000 years. But then the Anunnaki started to influence and corrupt the leaders of Atlantis. The corrupted Atlanteans, known as the Sons of Belial, initiated a conflict with Lemuria. About 25,000 years ago, Atlantis and Lemuria disagreed on how to rule the Earth. Atlantis wanted to dominate all tribes and civilizations worldwide. But the Lemurians wanted the Earth's civilizations to develop on their own, so they ordered Atlantis to leave them alone. Atlantis refused. Lemuria insisted. Atlantis chose war. The beginning of the war was the year 10,468 BC. In his writing, Plato mentions 9500 BC as the year that Atlantis was destroyed. An ancient historian named Hemus reports a terrible catastrophe that occurred in 11,000 BC. But how were these civilizations destroyed? Well, the Atlanteans had extremely advanced technology and weapons.
Their technologies and weapons were beyond what we know today. Flying crafts powered by fire crystals traversed the skies. Great energy beams harvested from the earth itself fueled weapons that could level mountains.
Lemuria was not as well armed and could not avoid war.
They burned the world with solar heat and tried to draw energy from each other. Rivers have been changed, and the height of the mountains and the strength of the sun have changed. There have been continents that have been flooded.
In the end, more than 60 million Lemurians died. The survivors took refuge in Agartha and later attacked Atlantis. The Earth became unstable as a result of nuclear explosions, and because of that, the Earth's axis changed and the poles shifted. All that remained of Atlantis are ancient structures like Stonehenge and the Great Pyramids. The civilization of Atlantis did not survive the conflict. But about 10,000 Lemurians did survive, and they rebuilt their civilization. But this time they did it in secret. And that civilization exists today, thriving, under a mountain in California. Mount Shasta in Northern California has become synonymous with the unknown. Many who venture close to the mountain report strange events, glowing orbs, unexplained voices, and a tangible sense of another presence. Mount Shasta is also considered a vortex, a place where the boundary between dimensions is thin. Native American tribes speak of its sacred power, a spot where the spirit world is accessible. Then there are the geological mysteries. Why does Shasta have such a complex structure and so many different kinds of rock? Why do some plants grow there that are found nowhere else? Where did those plants come from? Well, legend has it that some Lemurians survived the cataclysm. The survivors traveled to North America and brought with them plants and animals and technology. They then built a city underneath Mount Shasta. They called this city Telos, the City of Light, and eyewitnesses have described the city in detail.
As you approach the hidden entrance to Telos, an energy pulsates through the ground. There is a deep humming sound and a vibration that you can feel all over your body.
Once inside, you are enveloped by a soft light that emanates from the walls of the city. Telos is carved into 5 expansive levels, each one a labyrinth of corridors, chambers, and gardens.
The inhabitants of Telos are 7 feet tall and draped in flowing white robes. Despite their large size, they move slowly and gracefully. They are the Lemurians, the guardians of their ancient, lost civilization. Their technology is integrated with their natural surroundings. just as it did in Lemuria before the fall.
In Telos, they use crystal technology. Large crystalline structures serve various functions. They have healing chambers that resonate with frequencies that restore the body and the soul. They have crystal communication devices that allow mental connection across the entire planet.
Transportation within the city is achieved through levitating platforms that glide along magnetic lines, guided by thought alone.
At the center of Telos is the Temple of the Heart. Here, a large crystal pulses with a heartbeat, a rhythm synchronized with the natural resonance of the earth.
Residents of Mount Shasta claim to have seen tall beings wearing white robes walking at the foot of the mountain. Hikers have even followed the beings into caves, but when the hikers finally get inside the cave, it's empty, though some say you can still hear and feel the humming vibration. One eyewitness actually made the news in the early 20th century. In 1904, J.C. Brown, a British prospector, was hired by a mining company to search for gold deposits in Northern California. While investigating around Mount Shasta, he noticed an odd-looking piece of rock that didn't match the surrounding area. As he began clearing the debris and vegetation surrounding the rock, he found an entrance to a cavern system that led deep into Mount Shasta. Brown walked about 3 miles into the interior of the mountain through an array of crisscrossing tunnel systems when he began stumbling across pieces of gold. After the 11th mile, he reached a location that resembled a village. Inside the village, he came across chambers filled with gold and copper tablets. He found statues and spears and weapons, and he found skeletons. The average heights of these skeletons were around 6 foot 6 inches tall, and the tallest being 10 feet in height. Over the next few days, he took pages and pages of notes. He memorized everything that he could. And when he left, he covered the entrance so that no one else would find it. And Brown spent the next 30 years researching and tried to build a group of experts to embark on an expedition. He finally gained a following of about 80 people willing to join the expedition, including a museum curator and several scientists. He spent 6 weeks planning out the entire trip, and several individuals sold off their properties believing that they would soon become rich. Brown was worried someone would sneak into the city in advance, so he withheld a lot of the specifics regarding the location of the cavern system. He met with the team one last time to make final preparations and establish the time and place of departure, June 19th at 1 p.m. The day finally arrived, and J.C. Brown didn't show. And he was never heard from again. But the story of Lemuria is not only told in the West. The Tamil people indigenous to South India have a story of a lost continent that dates back to ancient times. The name Kumari Kandam was applied to this sunken land. The legend tells of an early Tamil dynasty known as the Pandyan Kings. They ruled over the now submerged Kumari Kandam continent before it was swallowed by the rising seas at the end of the last ice age.
Younger wet ass.
Dryas.
Whatever.
According to the stories, Kumari Kandam was once located in the Indian Ocean between India and Madagascar. This large continent was the cradle of civilization, home to the first people. The Pandyan kings ruled the entire continent from their capital city before successive floods submerged Kumari Kandam around 10,000 years ago. Is this just a Tamil legend, or is this actual history? Well, floods at the end of the last ice age, we have proof of that. But a lost continent in the Indian Ocean between Madagascar and India? That's so specific. There's no way there's proof of that, is there?
Is there? Is there?
There is. Imagine an ancient tropical land. Lush jungles stretch as far as the eye can see. Dinosaurs graze on treetops high above the forest floor, while early mammals stalk the dark ground below. This was Mauritia, a lost world forgotten beneath the waves. In 2013, scientists announced that they may have found traces of this vanished continent deep under the Indian Ocean. It had sunk below the sea millions of years ago when the continents were still joined as one supercontinent. Back then, South America and Africa hadn't split apart. India was attached to Madagascar, and Mauritia was squeezed in between. Mauritia was discovered by accident. Geologists studying rocks on the island of Mauritius, east of Madagascar, were confused. They found minerals too ancient to belong to such a young volcanic island. As they followed the clues, they found traces of a much older landmass. A huge mass of buried continental crust stretched across the Indian Ocean, a lost continent matching ancient minerals. The researchers named it Mauritia after the island that led to its discovery. But the location of Mauritius is exactly where some legends say Lemuria was. The details of the continent are still a mystery, with more questions than answers. Was it really an intact continent, or just a jumbled mass of islands? And what creatures might have lived on this island? And could some of those creatures have been the very early ancestors of the Lemurians? There is no hard evidence to support the existence of Lemuria or Atlantis. Everything we know about these civilizations comes from stories. And many of those stories come from unreliable sources like Madame Blavatsky, James Churchward, and Edgar Cayce. Daniel Fry, who claimed to have been abducted by aliens, probably wasn't. He failed a polygraph. He kept changing his story, and he lied about his scientific credentials. He also got caught hoaxing UFO photographs. So without evidence, places like Lemuria, the Land of Mu, and Atlantis remain nothing but myths. But the accidental discovery of Mauritius shows that some ancient legends may be based in truth. The discovery of the continent of Mauritius happened completely by accident. Bimini Road was discovered by accident. So was the Yonaguni Monument. The city of Dwarka is described in ancient Indian texts as a magnificent city that was a symbol of prosperity. It was described as an advanced, well-planned city with beautiful gardens and temples and palaces. But according to Hindu legend, thousands of years ago, the seas began to rise, and eventually Dwarka disappeared into the ocean and was lost forever. And for 1,000 years, the story of the city of Dwarka was thought to be symbolic. But in the 1980s, the ancient city was found, and is estimated to be around 10,000 years old, maybe older. In 2001, an underwater discovery was made off the coast of Cuba. Structures were found that at first were thought to be natural formations, but a submersible robot was sent to the site and found what's been described as an entire city. And what makes this find so extraordinary is that it's about 2,000 feet down. Scientists have said it could take 50,000 years for a city to sink that far. Now, even if it's not that old, there are blocks down there that are thought to be at least 6,000 years old, but nobody can say for sure. All of these discoveries were made by accident, and as long as people keep exploring the sea, there's a chance that Atlantis and Lemuria might eventually be found. And if we actually excavate the sites off India and Japan in the east, and Cuba and the Bahamas in the west, we may realize that Atlantis and Lemuria have already been found. Thanks so much for hanging out with us today. My name is AJ. That's Hacklefish.
Hey, what's buzzing, sexy cousin?
This has been the White Files. If you had fun or learned anything, do Hacklefish a favor. Like, comment, subscribe, share.
Okay, interesting. I mean, it wasn't that interesting actually. Let's watch some Vsauce maybe. Quantum computer, matter from light. Very ancient Egyptians, black. Let's watch this.
This
What happened?
video is brought to you by Atlas VPN. Hey number ones, welcome back to my channel. This is the Metatron speaking, and this is a platform where we value truth, facts, reason and logic. And if the truth offends some people, let them be offended. The question were the ancient Egyptians black is actually quite complicated. It's multi-layered. I'll try to bring as much clarity as possible in this video, as often the matter is rooted on a variety of political expectations, agendas, and the imposition of current perspectives and attitudes to depict and interpret past events in order to bend them in one's favor. A cauldron of personal bias and lies on any sides of the spectrum. Not how you do real and professional academic work. So, were they black, were they not black, does it even matter? Well, yes, it does. But it is only one among many other possible questions, such as how did they organize their armies, when did they reach the Bronze Age, how did they tackle commerce, what was their religion like, and a myriad more. All of these questions matter because they help us better understand a people, a civilization, their story. You create history by asking questions. Now, the question about their ethnicity becomes even more relevant when you are confronted by a group of people that tells you that the ancient Egyptians were black, the ancient Romans were black, the ancient Greeks were black, and if you disagree, you're a white supremacist and a racist. Trying to bend people into agreeing with you with the usage of insults and name-calling without evidence or in spite of contrasting evidence is ludicrous. It is a symptom of a feeble argument born from a weak mind. It is, however, important to underline that this is not a white versus black scenario. I unite with my white brothers, my black brothers, people of all ethnicity that value the truth, backed up by evidence, versus irrational, convoluted, and politically motivated, annoying people. Let me show you. Cleopatra. I think everybody has heard of her, but I don't know if you've heard that there is a group of people that say that she was black because she was the queen of Egypt. Egypt is in, Africa, therefore she was the queen of Africa, she was African, and she was black. And if you disagree, yes, you guessed it. Check this tweet out. I am not sorry to tell you all, but Rihanna definitely has that role owned. Gaga and AJ shouldn't have even been in the running. Honestly, if a black woman ain't playing Cleopatra, then nobody should play the African Egyptian Queen Cleopatra, period. It's very interesting that he would say that, first of all, because that's not a representation of Cleopatra, that's a representation of Nefertiti. Somebody else points that out under the comment section, and he responds by saying, "Huh, white boy, I know who she's dressed as. It was a reference point." We don't believe that. But regardless of whether he knew that or not, the statement is still very ignorant. Cleopatra came from a dynasty of conquering Greeks. Her ancestor was a general of Alexander the Great's army. She was born in Egypt, but she wasn't a native Egyptian. She was Greek, her father was from Cyprus, and therefore she didn't share the same phenotypic traits with the local population. All rulers from the Ptolemaic kingdom in Egypt from 305 BC to 30 BC would have been Greek. We don't know exactly in details what she looked like. She was described as being very attractive and very intelligent, but we do know that she would have looked like a Southern European, a Greek of the time. Now, I happen to be a Southern European. I'm from the Mediterranean. I'm Sicilian. I happen to be on the pale side. Maybe she'd look like me. Maybe her skin would have been a bit more tanned, perhaps olive color. Still, she wouldn't have looked like a native African Egyptian. And we've got statues that show her hair and face structure and nose structure together with some coins. Again, clearly Greek. Saying that Cleopatra needs to be represented by a black actress because she was from Egypt and she was the queen of Egypt, it's like saying in 300 years from now that George Washington is supposed to look like a Native American because he was born in America and he was the president of the American United States. Okay, fantastic, but what about all of the other pharaohs? What about the actual general population, the Egyptians? What did they look like? To answer this professionally in the most accurate way possible, we have to examine Egyptian art, understand how they utilized color to represent themselves and their neighbors, and we'll address the term Kemet, the word the Egyptians used to refer to Egypt. We'll talk about an article that deals with the first successful genomic testing on ancient Egyptian mummies, where the mitochondrial genomes of 90 mummies were taken, and we'll discuss the results together. You'll find links in the description below for further reference. This and much more after a brief word from our sponsor. And now I'd like to take a moment to mention the sponsor that made this video possible, Atlas VPN. But what is a VPN, you ask? A VPN is a virtual private network that makes choice integrated. I am living a 30-day money-back guarantee and enjoy your safety. Welcome back. The only way to answer this is to make sure that you and I both know what we mean exactly with the word black. And I've noticed that some academics these days love dancing around this one because it's controversial and they don't want to offend anyone. So what do? They say, oh, but the ancient Egyptians didn't have these modern concepts of black people and white people. That's a modern construct. So they were neither. That's dodging the question. So let me be 100% crystal clear here. Did the entirety of the population of Egypt, or the majority of the population of Egypt, look like this handsome man? No. The ancient Egyptians were a multi-ethnic African civilization. It was multi-ethnic because of its very geographical position, a connection between Africa, the Mediterranean basin, and Asia, a strategic location on the crossroads of continents. The Egyptian civilization flourished around the Nile River, which was a cultural conduit of civilization. There is diversity in the skin of the Egyptians. Through time and space, the ethnic percentages will differ depending on what area of Egypt and which era. Egypt is not disconnected from the rest of Africa, and it is absolutely imperative to fully appreciate the complexity and connectivity of such a geographical area. However, the ancient Egyptians did acknowledge and recognize the physical differences between them and their neighbors, specifically utilizing skin tone as one of the major distinguishing factors, already disproving this idea pushed by some people that the ancient Egyptians didn't even see a difference in skin tone and that that's only something that we modern people see. Probably humankind has been noticing that difference since prehistorical period. Of course, the ancients didn't share the same beliefs and classifications as 19th century, 20th century, and 21st century people when it comes to the words that we use to identify people and how we use them. Even in my case, I had recently immigrated into the United States of America, and when I was filling in my immigration sheets, they asked me to put the ethnicity section, and when I asked, so what should I put? They said, just put white. Well, if this was the 1920s in the same United States of America, they would have had me write either Italian as a separate ethnicity, or, as it did happen, black, depending on, I suppose, on your skin tone, maybe. These classifications are indeed fluid, but I think we all know what we mean when we say black. Like this guy. Here is what the Egyptians said. Look at this image. To the right, you see how the Egyptians represented themselves. The black gentleman is representing a Nubian, basically a member of the very prominent and very powerful and advanced kingdom of Kush, which was south of Egypt. And those are representations of an Asiatic and a Libyan. Of course, it's important to take into consideration the cultural and commercial and religious exchanges that happened between the kingdom of Kush and Egypt. Of course, a certain percentage of Nubians, which will differ depending on which area of Egypt we are talking about, will have lived among the Egyptians. But the Egyptians do represent themselves with this image, with this specific color. And with color and art, we enter a whole new range of topics that I'd like to hopefully simplify for this video. How did the Egyptians use and create color, and why do Egyptian women almost always look lighter in skin than their men? And was there any inner and sometimes hidden meaning within color itself? Well, each color was created by mixing various naturally occurring elements, and each became standardized in time in order to ensure a uniformity in artwork. An Egyptian male was always depicted with a reddish-brown skin, which was achieved by mixing a certain amount of standard red paint with standard brown. Experts say that this color was chosen because it was a realistic representation of the average Egyptian. Women's skin instead was most of the time represented with a mixture of yellow and white. And the reason of the explanation to this is because women tended to work the field a lot less than men. They tended to stay inside, and therefore their skin was lighter. If the difference in skin tone between men and women is darker or lighter depending on how much time they spend outside, then it suggests that even the darker tones we see are mostly a tan rather than the actual natural color that all Egyptians would have. So it is possible that a light brown would be a good representation when it comes to what the ancient Egyptian skin looked like. If they were all black in the sense of a Nubian, they would not represent the Nubians and themselves differently in art, and of course a Nubian's skin color is going to be black, whether he stays inside or outside. The gods are represented with many colors, but they are symbolic when it comes to their skin. They can have a red skin, which usually has to do with aggression and evil in a way, although it can also symbolize life. Some gods have a blue skin, which represents protection and wisdom. Other gods have a green skin, such as oftentimes Osiris, because it's a connection to the afterlife. And when it comes to black skin in Egyptian art, even though it does have a connection to death, which is why we sometimes see gods such as Anubis having black skin, it was not connected to evil. Red was. So what about the term Kemet? Well, Kemet has been used again by some people trying to push this idea that all Egyptians were black and it was a black civilization, because they say that it means the land of the black, and therefore if the Egyptians refer to their own land as this is the land of the black, then it means that they consider themselves black. But it's interesting that the people that I've read in forums, they say this, but then a minute before that, they actually say, oh, but the Egyptians did never refer to themselves or other people as black and white and brown. That's a modern construct. And this already shows you lack of intellectual honesty, because you can't say that the Egyptians didn't use black, brown, and white to describe people, and then a minute afterwards use it when it comes to the translation of the word Kemet when it's convenient to you. Kemet meant black land. meaning that was the color of the land, the soil. Scholars generally believe that this name derived from the fertile soil that was left over when the Nile flood receded in August. Considering the fact that the very people that pushed this idea of all the ancient Egyptians were black did say on multiple occasions that the Egyptians did not use color as a word to describe people, then I would say on their own terms that it is more probable that Kemet referred to the land being black, not the people. When it comes to the analysis of DNA, there are several methods the scientists can use, including the direct PCR, a method of DNA amplification directly from an animal or plant tissue sample without performing DNA isolation and purification steps. This technique greatly reduces experimental time and cost in genotyping and high-volume projects, but it does come with issues surrounding the authentication of the retrieved DNA and the potential contaminations inherent to this method. Say the hot Egyptian climate, the high humidity levels in many tombs, and some of the chemicals used in mummification techniques, in particular sodium carbonate. All of these contribute to DNA degradation and are thought to render the long-term preservation of the DNA of mummies improbable. Now, some of you might ask, why bother with ancient mummies at all? Why don't you just check and analyze the DNA on modern-day Egyptians? And the thing is that in order to do that, you would have to have a perfect genetic continuity over 1,000 years, millennia. And that is very improbable considering the recent population admixtures from both other areas of Africa, Europe, considering Roman and Greek colonization, and the Islamic expansion. Even without genetic proof, it would be very unlikely to expect such a perfect continuity between ancient Egyptians and modern Egyptians, and this study, in fact, demonstrates so. 166 samples from 151 mummified individuals were examined for this study, 90 of which you will find in the later analysis in the supplementary data 1. According to radiocarbon dates, these samples can be classified into 3 time periods: pre-Ptolemaic, Ptolemaic, and Roman period. Scientists found that the 3 ancient Egyptian group clusters supported a certain level of genetic continuity over 1,300 years, but showed a higher affinity with modern-day people from the Levant and the Middle East, an affinity supported on some of the individuals with the find of the Y chromosome haplogroups. On the nuclear level, scientists joined their data, called the SNP data, together with both ancient genomes and modern-day genomes, and found that the ancient Egyptian samples were further away from modern-day Egyptians and closer to the modern-day Near Easterners and Europeans. The scientists that performed these tests were extremely professional, but you can imagine that both Afrocentric groups and Eurocentric groups tried to use these and tackle these differently, with Eurocentric trying to then prove that the ancient Egyptians were European and they were white, and Afrocentric trying to instead saying that these mummies probably were just foreigners and were not actual Egyptians. I do think that the truth lies in the middle, meaning that even though we do need to accept the fact that this test only deals with the mummies found in a specific area in Middle Egypt, therefore it does not necessarily represent the genetic makeup of the entirety of the population of all of Egypt, and of course there would have been variety, but it does strengthen the idea that Egypt was a multi-ethnic society, and some of the Egyptians that lived and were mummified in Egypt would have been considered from a modern-day standard perhaps even white. Does that mean that the ancient Egyptian is a white or a European civilization? I don't think so. I think that more studies on mummies will probably reveal that the southern part of Egypt had a higher percentage of individuals.
So in general, saying that no, that's bullshit, which is not surprising. So now you see AI is pretty neat. It makes the impossible suddenly concrete. But don't ever worry, there's no need for alarm. It only does what its human creators charm. That's fine, I guess. So what should we do for this one? What should we do for this one? Let's see what we got here. China's new giant infantry vehicle is a nightmare. Should we watch that? No. The truth they won't tell you. The Woman King. And their lies vs historical truth. Announcements. What is that? What is that? Oh my gosh. Oh my gosh. What the hell? Oh my god, it's terrible. This guy was really lucky there. Oh my gosh. Crazy. The other clipper was back. Remember it. Alright, so we are in page 11. We have one more page. Let's just end the live. Thank you everyone for joining. Hopefully see you next time. Bye. Okay, let me end this live too.